So I think we've started to progress beyond it. Just everybody kind of gets LLMs, the chatbot interface. Now the concept of agents is becoming popular. Where do you see agents delivering real value in the AEC industry within the next year to year and a half?
Yes, AI is nice to have. It helps us. We dictate what it does, but it could save us a lot of time. But what if we didn't have to tell the AI what to do every single step of the way? And that's an agent. So an agent, you sort of set it off on its mission, and you have a whole team of agents. So every person, imagine if
Agentic AI is everywhere right now. But here's the real question. Where is it actually creating value on AEC projects today, and where is it just hype? As firms rush towards digital twins, AI agents, and simulation-driven workflows, many leaders are discovering that more technology does not automatically mean better outcomes. In this episode, I'm pleased to be joined by Sean Young, Director of AEC Geospatial and Enterprise Industry Marketing at NVIDIA. We'll speak about what truly qualifies as digital twin, where agentic AI is delivering practical impact, and how emerging demands like data centers and energy constraints are reshaping the types of projects AEC firms are delivering. If you're trying to make smarter technology investments, lead teams through rapid change, and turn AI from a buzzword into real project performance, this is a conversation you will not want to miss, and is one that will help you focus on what actually moves the needle. With that, let's jump into today's episode. It's now time for our conversation of the week with Sean Young. Sean, thank you so much for taking the time to join us today on the show, and welcome.
Thanks, Nick. Nice to be here.
Absolutely. And we got an action-packed episode here for you guys, right? And I'm sure everybody knows the company that Sean's at, so we're just gonna skip that and just get right into it. So Sean, could you tell the listeners a little bit about yourself, how you got started in the 3D visualization, simulation, and the AEC technology space? A little bit of a long question, but we'll let you get started to let the audience get to know more about you.
Yeah, I'm happy to. I'm not the interesting story here. NVIDIA is, but anyhow, I got started in software product management. I've been in 3D software for architects and engineers my whole life, my whole professional life, and I worked at Autodesk and then got into hardware with HP and now NVIDIA. Always focused on these markets, and NVIDIA. Do you want me to talk about NVIDIA?
No, I think everybody is dying to hear, but go right ahead.
Okay. Well, so, NVIDIA has also always been focused on these markets. NVIDIA started as a gaming company for PC games and quickly started also taking care of customers in architecture and engineering. So I'll give you some context. NVIDIA got started because games didn't run well on CPUs for, computer-based games. And the reason is because the CPU has what are called cores, and they have a limited number of cores. So every device you have is a CPU, and those CPUs have maybe 6, 10, 12 cores normally, like your laptop or your iPhone, and each core could run a different thing. So one runs the operating system, one runs Outlook, one runs Revit, et cetera. And so eventually you run out of cores pretty quickly. Now, what's really interesting, some of these applications can do computing tasks take another core to do a computing task, or even take multiple cores for things that can be broken down and split onto cores. Things like that are the computationally intensive, algorithmic computing. So physics, simulation, any type of math computation, which includes both of those things are captured in real-time ray tracing period. Mathematically intensive, can be broken down and split into multiple cores. But guess what? In the CPU, you run out of cores, so you can't really do that very effectively. So NVIDIA made the GPU and made it for games. And if you think about a game, the game has, a frame, a minimum 30 frames per second. So lots of frames. And each of those frames have, can be divided up into image blocks. That's the smallest level, a pixel. Well, what if you can take those blocks and split them up into multiple cores, process them independently, and bring them all back together again, and just put it in the right place on the screen? That's exactly what NVIDIA did with the GPU. And you just cannot do those things on the CPU. And it turns out that, of course, many years later, AI is leveraging that capability, because AI wants as many cores as possible to do complex calculations in parallel. And so a lot of these AI training can be parallelized across all these GPUs at the same time. We work with all the software companies in our industry: Bentley, Nemetschek, Trimble, Hexagon, Autodesk, et cetera. And we work with their development teams to help them accelerate their software where it can be accelerated on our GPUs. And we provide a toolkit around the GPU to make it simpler for any software developer, not just the ones I named, to write software for our GPU. And that's called CUDA, CUDA. And if any of your listeners are studying computer engineering, computer science at school, I'm certain they have the option of taking a CUDA course. It's quite widespread. And so in general, if you want to accelerate your software, and that includes doing AI, then you want to do any of that stuff in real time, it needs to be accelerated, then you want to use a GPU, and CUDA is the easiest way to do it. That's basically NVIDIA's history in this industry.
So humble beginnings, right, in gaming. And now you guys are at the forefront of let's call it this AI revolution, because what's happening today doesn't happen without you guys, right?
Well, yeah. Well, there's a couple of reasons for that. One, we enabled the technology at the foundational level. Two, our technology is quite widespread, and there's lots of developers out there in the world who know how to use CUDA and include it in their code, so they know how to accelerate. When AI started coming around, and there was a massive amount of computation, the computer was really the bottleneck, because it just requires a massive amount of compute. And NVIDIA made that massive amount of compute accessible in the most affordable way, in terms of both the cost of the equipment and the cost to operate the equipment, which is power and cooling, and in the way with the least friction, because there's all these computer scientists out there that know how to use CUDA already. So it's just a natural thing to use CUDA and NVIDIA GPUs with AI. But since then, it's really not a simple problem computing at that scale. And so it's not just the GPU that goes into the machine, like your workstation. It's the GPU working with the CPU, working with the memory, working with the networking. The networking is hugely complicated when you're dealing with this kind of scale, and managing the whole system as a system is hugely complicated. So NVIDIA has done what's called extreme co-design to tackle, instead of leaving it to somebody else to figure out how to do that thing, we do it ourselves. And because we have visibility, we talk to the customers, we have visibility on the end-to-end workflow. So we develop what's called the full stack, putting all this stuff together into the most efficient, from an energy perspective, consuming energy, and I'll get into that, architecture. And that includes a lot of software to run these things, software for them to talk to each other. Now we have a GPU and the CPU on the same chip, and that creates a lot of efficiencies. We have chips for networking. We make that CPU chip, and we have software that goes with all this stuff, and we have our own networking hardware as well, because frankly, we're trying to solve the most extreme problems using full system thinking, and it takes that ability to understand each element of the system, systems engineering, to solve the problem.
Sean, speaking of systems, we'll bring it back to AEC here. It's like, what is a building, but a system of different parts, pieces, components that we try to kind of digitize into a term that's commonly referred to as a digital twin.
Mm-hmm.
So I think it's more of one of the hot button topics. Depending on who you talk to, you might get a different answer and opinion. But in your opinion, what definition actually matters for AEC leaders, and then what doesn't qualify as a true digital twin?
Yeah, well, digital twin is a term that's thrown around really loosely. I think, unlike BIM, which I think has a pretty clear definition in everybody's mind, digital twin could stand for a lot of things. Like some people say, here's a rendering, that's my digital twin. Some people say, here's a BIM, that's my digital twin. Here's a point cloud, that's my digital twin. NVIDIA, so I don't think there's a right or wrong answer, because who am I to say what? I could just tell you what we at NVIDIA consider a digital twin, which is something quite different than all those other things I said. What we try to accomplish with the digital twin, and we need to accomplish with our digital twins, is a complete simulation of reality.
Mm-hmm.
And reality in our world is grounded on physics. Without physics, you don't have reality. So our digital twins are focused on physics first. It's not about, so I would say, like, if you showed me like a real-time rendering, or did a real-time fly through of a building or whatever, that's on a digital twin, because it's a real-time rendering. It's a visualization. It doesn't have any of the physics in it. So what we try to do with a digital twin technology is enable our partners and our customers to build their own digital twin solutions that account for physics. And there's two reasons why we need to do that. The first reason goes back to the origin of why we started building digital twin technology. And the origin happens to be autonomous driving. And we started creating, we do a lot of R&D in autonomous driving. We work closely with Mercedes-Benz and a number of other automotive manufacturers on their autonomous driving solutions. We have our own fleets of cars driving around doing reality capture and converting that to what's called synthetic data for training. Because you can never, in a car you see the cars driving around, well, you've all seen the Google cars, but now you have similar types of cars driving around, capturing the roads for training autonomous driving. And you have to do that, like, for every city and, highway and stuff. But the problem is the car drives down the road a certain time of day, and it's not going to keep going back and forth all day long. It's never going to get every possible condition on the road. So you have to create those conditions in a synthetic environment. And those conditions are always going to be physics-based. Like, for example, the car needing to slam on its brakes. How long does it take to slam on its brakes? Does the car skid out in certain conditions, like if the road is wet or icy? What if there's an obstacle in front of the car, like a kid? What happens there? So you calculate what's the distance that the car needs to start braking. That's all physics-based stuff. But you need both the physics and you need the environment. Now, the car understands the world through its sensors, which are cameras or radar or LiDAR. So you have to show those virtual sensors where you're training AI in this virtual environment, the world it's going to encounter in the real world, which means the renderings need to be physically accurate, because if the lighting's off, the shadows are off, when it gets out in the world, it's not going to understand what it sees if it's trained on like something that doesn't look right. So, the physics come in terms of the Newtonian physics, how the world works, but also in terms of the visual physics, the photonics of how the world looks. The car needs both of those things together. And now you can apply that to any use case where you're training an AI. And that could be as simple as just on a construction site. You have fixed cameras around the site, and the cameras are watching for safety incidents, for PPP, progression monitoring of construction, comparing as built back to BIM, etc. All that AI needs to be trained. And the way to do it without putting people at risk, especially when there's no building there and you have to train an AI before the construction starts, the way to do it all is in a digital twin. So that I said it was two reasons. So the first reason is that all of that process is called synthetic data, and it's synthetic data generation for AI training. AIs need a lot of data. That process develops a lot of data. The other reason is simply for people, not AIs, to see everything, all the data in one place, and now understand it from a physics perspective, not from a look perspective, although that's part of the thing, because our eyes help us understand, but we also want us to understand the physics. How fast is that going to go? What happens if the road conditions or the earth conditions are this way, and I want to bring this heavy truck into the construction site? What's going to happen? So on and so forth. And if you apply that to an airport as an example, like, where you have a massive amount of complexity in terms of people moving around, in terms of planes moving around, in terms of cars moving around, and then you also have all the plumbing and electrical and lighting and everything. And you need to, figure out traffic ways, laneways, security checkpoints, all of that. You want more than the visual. You want the physics to figure it all out.
Sean, let's talk about this concept of a minimum viable twin, because what you're talking about here, essentially creation of synthetic data, that's got to be like computationally intensive. And perhaps depending on like the stage of the project or whatever you're trying to accomplish, maybe there could be a point of too much. So can you talk about like minimum viable twin that essentially allows the user or whoever's trying to build it to get what they want out of it without overdoing it?
I mean, that is really contextually specific, I think. Like, for example, if you're doing defect detection, synthetic data, which is just trying to understand if an object is rusty, you could just, potentially not have the geometry of the object, but just train an AI to understand rust and just show a bunch of different images of rust, whether those are real photographs or synthetically generated rust. But you also have to generate rust and not rust. Just like if you're training an AI to understand between cat and dog, you have to generate cat, dog, and all sorts of permutations in between. So eventually the AI learns to understand that it's a dog. And even what type of dog. Yes, it's rusty. How rusty is it? Does it need to be serviced or not? So it really helps, in my opinion, but I'm not the expert on this. But as far as I know, it helps to have a little bit more context. The more context, the better, because then, yes, it might take longer training time, but then the AI is less likely to make mistakes and is more information. It's the same thing when you give a prompt in ChatGPT. The more context you provide the prompt, the better the response is going to be.
And like you said, it's context dependent, project to project, use case to use case. So that's the thing about this industry, right? There's never any one simple answer, and it depends is typically what we come up with a lot of the time. But so Sean, then my next question, another very interesting and hot topic here is agentic AI. So I think we've started to progress beyond it. Just everybody kind of gets LLMs, the chatbot interface. Now the concept of agents is becoming popular. And you can hear a lot about it, from whatever source of news or media you're looking into. Where do you see agents delivering real value in the AEC industry within the next year to year and a half?
Yeah, in my mind, the chatbot is kind of like the proof of life, but the agents are where you start to get productive because the chatbot moves at the speed of humans. And so, yes, AI is nice to have. It helps us. It actually, we dictate what it does, but it could save us a lot of time. But what if we didn't have to tell the AI what to do every single step of the way? And that's an agent. So an agent, you sort of set it off on its mission and you have a whole team of agents. So every person, imagine if you in your job as an engineer had a team of 20 people, working for you. What would you have them do to help you out? And that's exactly what you get with agents. Well, the first thing you would probably tell them in, the complex world we live in is you guys have to work together. And I don't want to have to tell you every step of the way what you need to do together. And there's going to be a lot of handoffs of information, a lot of knowledge sharing. You do this part, you do that part, you do that. And there may be some dynamic actions required because you're going to encounter conditions that we didn't expect. And you don't want them to come back to Nick and have to have Nick's permission or instruction for everything. That's where the agency comes in. Included in that is sharing information, developing things, checking what's going on in the world, whether that's sensors, cameras, checking the internet for certain types of data, opening up your legacy software applications, all 100 of them, and extracting data and sending it to another agent, generating data inside of those applications, going through the application APIs, generating additional data through LLM or through diffusion or some other method. Generating geometry is possible independent of those applications. There's tons of different things that can get done. In terms of how that gets applied, I mean, the holy grail is like, here are the requirements, the RFQ from the customer, generate the full construction document.
Yeah.
We're ways away from there. But along the way, the elements that need to go into that are starting to happen. I'm starting to see all these different elements. Like, for example, physics-informed neural networks, like using AI to predict the physics. For example, we've seen some tools that are able to generate geometries. The highest quality geometries are being generated from the traditional application. Like, for example, you go into AutoCAD, you have an AI go into AutoCAD and generate or Revit or MicroStation or whatever, and generate some geometry. Okay, instead of you having to know exactly how to push all the buttons to do that geometry generation, you can just say, I need a building this high with this many windows, and boom, the AI understands how to use the application API. This is called MCP, Model Context Protocol, and generate the geometry. But then you say, well, what would be normally the next step? I'd need to take that geometry and do some sort of FEA for structural simulation, because that geometry may not work for the geographical conditions. Well, what if you just had the AI do that for you? Like, do that first, or do it as you're developing the geometry. So the geometry that comes out of the process has already been pre-checked against, an FEA or a predictive version of FEA.
Well,
so the physics part is huge.
In the industry today, like that might be a handoff between like an architect and a structural engineer. Well,
yeah. Back and forth and like 200 pages of slides. Here's why this structural doesn't work. And like, if you look at this part and this part, and do you understand what I'm saying? All right, we'll take another hour meeting so I could explain it to you. We'll get some other people involved. All that goes away. If you the geometry that comes out is been through a structural analysis process before it was even generated.
In the AEC industry, skilled project managers are the backbone of success. EMI's AEC PM certification offers tailored training, ongoing support, and exclusive access to premium content that keeps your team sharp and effective. From foundational training to advanced leadership tools, set your team apart with certified growth. Learn more at aecpm.com. That's aecpm.com.
Which is really exciting because, and I mean the concept of artificial intelligence, right? Because we all only have we have a limited bandwidth and a limited area of expertise, but you're able to do and learn so much more through, right? Essentially, all of humanity's knowledge in our pocket now, right?
Yeah, and that we have that already, with the LLMs, these foundation models from the labs. But the question is, how do you harness them to get things done, to help us?
And it sounds like teams of agents, like managing them, it's not all that different than managing teams of people. Is that directionally correct?
I think it's directionally correct. I mean, our CEO likes to joke around that, the future HR department is today's IT department. You're going to have HR for regular people and IT for, your agentic people, your AI agents. And that, I find that to be, incredibly empowering, because if I, 20 people working for me, I would just get a lot more done, 20 clones or whatever, as long as I don't have to tell them what to do every step of the way, because that slows me down.
And right, I'm sure they can come ask you questions, they can come ask for context and clarity, but they just figure it out ultimately.
They figure it out. And that's the key thing, like context and questions. That's it. Like reinforcement learning, getting reasoning on inference. This is starting to happen now. So, and people sometimes say, well, how can I trust it? Because it seems like a bit of a black box, but that doesn't have to be the case. You can ask the AI to leave a paper trail, sort of like a history, of your modeling for every step of the way, and so you could see how it's doing its reasoning and getting to its results. And you use that, there, of course, you don't sort of let it, roam wild on day one. You want to verify its accuracy and, consistency and stuff like that. But the AI showing you what it's up to every step of the way really, I think, helps you have build some confidence in what it's doing.
Which, Sean, is a great segue into our next question, which is about trust and governance. And this could be a really foreign concept to some people, right? Especially if they're not as involved in the day-to-day like we are of AI and everything that's going on. Because in traditional, right, command and control, top-down structures, right, you got a boss's boss, and decisions come down to people. Somebody's responsible for signing off on something or whatever the case may be. So then take that framework of how we operate as humans and bring it to the agent world. How do you view trust and governance, and basically like who signed off on what?
Yeah, well, I'd say for the time being, like I'm not an engineer. You're PE, right?
Mm-hmm.
So you, I'm sure, have to sign off on work that other people do, like especially for these massive projects.
Absolutely.
So in the world of AI, you're just signing off on work that these AI agents do, and in addition to some other people. So you probably, as the PE who's going to sign, you want to go back and look at history and understand how they came to their decisions. You want to study their output and use your own, in knowledge and experience to determine if the same way you would with people. And if anything, you get more transparency with the AI process than you get with people, because you're never going to get a person to document every single decision that they make. But AI can do that for you.
And you bring up a great point. And, for anyone who's interested, so each professional organization or society, think of like AEC, ACI, et cetera, they probably have some sort of mission statement or policy stance on the use of artificial intelligence, particularly when it comes to the licensed engineering. So if you're curious, take a look at that, just whatever your governing body is. But you bring up a great point, Sean, that I'd thought a little bit about but never explored, because you can get into a level of detail that's probably just not possible with your human coworkers. So,
and also, let me just say, also alerts along the way, you don't have, you might want checkpoints, and with humans, time varies, things happen. I got to go get the kids early at school or whatever. So somebody misses with AI, that's never going to happen. Right. So in terms of your defined milestones along the way and the documentation you're expecting to receive, so you can get up to speed, you can keep up to date on the project as it goes through the process. You're going to get everything you need as you need it in the format you need it.
And you can, right, at any time, it doesn't matter if it's 2 in the afternoon or 2 in the morning, you can just ask whatever question's on your mind.
That's right. You ask whatever question you want, and everybody working on the project who's an AI answers you.
And it's not like it, and it may not take, hey, I need 24 hours to get back to you. Need a little bit of time, right? We're not going to say it's going to be instant, but.
And for all of us who work with people, what's really interesting about this is we don't always like the way different people communicate, or it's not always what we need at the time, right? The way one person wants to communicate and what we really hope to get. That's not going to happen with AI. AI is going to know exactly the style you want, in terms of, you want it 3 bullet points instead of 14 paragraphs. You're going to get 3 bullet points instead of 14 paragraphs.
And there's this meme out there, and I'm sure you might have seen it, where it's kind of like leader versus boss, and on there the third panel is boss with AI and leader with AI, and it's the cool, and I'll have to send it to you. But I think it's really funny because it's definitely a different style of management and working with agents instead of people, and it doesn't have to be all, some individuals might make it doom and gloom, but I think it's a really positive and interesting outlet, right? Because never have the people been so empowered to do more with less, essentially.
Yeah. And speaking of that, I think the important notion here is two things. One, to do a really good job at what it's doing, AI needs to understand the way you work. So you have to sort of train it. Like, and you can think, and we talked about training before with training cars to drive themselves. But like you can think of AI as like, a brain that doesn't know anything yet. And like a kid, you've got to teach it. And so how do you want to teach it? And what do you want to teach it with? Well, in the case of the AI that's helping you with your business, you want to teach it about your business. So you need to
Mhm.
give it your data. And if like you specialize in a certain practice area, or if you have special techniques or 50 years of doing something a special way, that's different from your competitors, and you probably want to teach the AI all that stuff. And the other important thing is it's not all the AI that you're going to use going forward is going to fall from the sky. Like somebody else is going to do it for you, like one of those traditional software companies I mentioned at the start of the call. Yeah, sure, they're all working on AI, but this is the first time where you know technology is incredibly disaggregated. Means like you're going to use lots of different pieces and democratized, because you could just do this yourself. Like any of us on this call can go and do some vibe coding and write our own thing in like 30 minutes. And shockingly, that's not a lie, you know,
No, it's
like
not.
I don't program. I can go, if I had 30 minutes, I can go and, make some app, for me. And it's wild, and I did it the other day, and I'm looking at, I didn't ask it to start, I just wanted a table, and it started doing all these things in Python, right. I did Perplexity. It's like writing all this Python code. I'm like, whoa, at the end of the day, I get a table, and that's exactly what I wanted. But the table's filled with all sorts of data from all over the world, including some of my own data that I have, internally at NVIDIA that's not accessible to the world. So there's a whole new world here. It's really remarkable. And I think, in terms of thinking about your job as an engineer and,
Mhm.
being an engineer and just doing engineering work with software that somebody else made that you swear at all day long and pull your hair over. Well, hey, maybe you want to do your own thing.
And I'll have to send it to you after we vibe coded. Super simple construction technology translator. So it just takes client inputs and then translate it into construction technology jargon, which I got a good laugh at. But it's cool, and I think like to your point, right? If you're an engineer and you're used to working in spreadsheets, great. Like you can hop on Replit, Lovable, any of these other vibe coding platforms and make tools that are more specific to like the way you work in your use case. What I will say though is when it comes to scaling that to the enterprise, I think that's a different discussion. Like personal productivity and enterprise productivity. What do you think?
I don't know. It's a really interesting question because, the question is, I guess, is the enterprise going to restrict you to only using, official certified enterprise software? Or is it going to want to encourage you to do your own vibe coding and make your own things that fit for your workflow that may not be relevant to somebody else? And then if you extend that, it's like it comes down to the agents. Why shouldn't you go and be able to create your own agent? And you have it's just like for an Excel script or something where you have an idea for a script and you write it. And so the official tool you're supposed to use, the corporate tool, is Excel versus another spreadsheet, but you're not being limited on how to script it.
Mhm.
So I wonder if AI can be something like that. Like you have these official ISV applications that you use, and maybe some official AI platforms that you use, and on those things can work together, and you uh, figure out how you want them to work together, and you write that yourself. There's a library of agents you can get from corporate IT and from your team, but why can't you do some of those yourself? And the interesting thing is you don't have to go off the reservation because you can use AI that you create with your traditional software applications. Just some of those hair pulling things that you wish can be automated or accelerated or whatever that the software company didn't think of because they don't know the way you work for that specific thing, or you're the only one who does that. Well, you write a tool that, like a plugin,
Mm-hmm.
you don't have to do the coding. You just speak English and say, I want a plugin for AutoCAD that does this, and bang, you get one.
And this is one, KP talks a lot about, is like, the keyboard being dead. And that's, not entirely true, but I find myself, right, more and more text or speech to text, but the computers now understand us, and it's not just English. Like, you can speak any language, and for the first time in history, right, we don't have to know the computer's language; it knows ours, which is also pretty incredible.
Yeah, English to API. Yeah, API is just another language.
And it's
application protocol interface. I'm sorry to use it jargon.
no,
it's the way that you speak programmatically to an application.
But you've brought up a great point that I hadn't really pondered too much, which is, right, like the organization or the enterprise level sets like the guardrails and the sandbox to play in, and you just go to work with what you have. So, like, for example, you can go to something like Microsoft Teams and make agents based on like the parameters that your organization has given you. That's definitely one example. And if you can get those to, for example, right, like, just go do your day-to-day tasks and your, disperse, number of different softwares, whether it's from, let's get Autodesk product, a Bentley product, a Microsoft product. And you can essentially take the workflows and all the stuff that's in here that, man, it'd be great if I could just have 20 people working under me. Boom. It's now available to you. Easier said than done, right? Of course, but it's possible.
It's possible. And, and so a lot of what we just talked about is individuals going at it alone, but there's no reason for that to happen in an organization. Get together with your peers, have like interest groups, birds of a feather, and figure out what kind of agents can we all sort of contribute to, or at least contribute to the requirements for those agents. It's a whole other world. And sure, share that with your software provider. And maybe, the more they know about what you need, of course, is always the case. But like, you don't have to necessarily wait, you can do it yourself.
Excellent. So now, Sean, let's zoom out to like the thing that makes this all possible, which is the infrastructure, more specifically data centers. So, right, we know that for everything that AI needs, it's relatively resource intensive, and data centers make it happen. So how should AEC leaders think about data centers as a new core project type? And then what's changing in the way we deliver those, from site selection, delivery timelines, risk, stakeholder expectations, and anything else you can think of?
Yeah, it's a really interesting question because, in fact, like, data centers are becoming the most important practice area for this industry.
Mm-hmm.
I'm hearing some of the customers I talk to say it's like up to 1/3 of their revenue. And at the same time, other sectors are really dropping fast, like regular commercial Class A stuff. So NVIDIA data centers are actually going to be quite unique because, how I was talking about at the start of the call, how we do the whole system thinking and extreme co-design. All of this we do for two reasons. One, to get the maximum performance possible, like price performance. But the key ingredient into price performance, one of the biggest costs and actual supply limited ingredients, is power. So what goes into a data center besides our computers is power. So the key equation for having a successful data center is converting the power to compute output, not compute input, because computers have a specified, voltage requirement, but it's what you can get out is really important in AI. That is basically tokens. That's one way to think about it. So an interesting metric is watts to tokens conversion. Now, the way we do extreme co-design at NVIDIA on all the parts that go into the thing, the computer with the networking and everything, it basically gets dropped off in a rack in the shell of the data center. Right? So if you go build your data center without anticipating this really unique equipment from NVIDIA that powers at 800 volts, that cools at 45 degrees Celsius, quite different than other racks.
Mm-hmm.
And you just expect to drop it off in a generic data center and have it work optimally, you're mistaken. And that is a fundamental change to the way data centers are going to be built, because it used to be the case that you can just go get the land power shell, build the shell generically from an MEP perspective. You have you have your air cooling and you have your electricity, and just drop. All right, it's ready for whichever data center operator wants to put in their computers, colo or neocloud or hyperscaler. And that is no longer the case for those who are, and there are many of them who are doing like wall-to-wall NVIDIA. So what we're doing now is working with the industry to extend our co-design to include the building, not just the building, but the energy supply, the land power shell. And the critical ingredient there for everybody on this call is MEP. Because if you get the MEP wrong, then you're going to get the whole system wrong. And that's going to become the weak link in the chain. And those computers aren't going to get the energy efficiency that we need. And that's why we cool at 45 degrees Celsius. That's why we water cool, because you water cool because you don't take in electricity away from the compute. You cool at 45 degrees Celsius instead of colder because it needs less energy to cool, so on and so on. Everything we do is towards that objective. So now what we're doing is working with the MEP manufacturers like the Schneider Electric, the Vertiv, the Siemens, etc., the Trains, the whole way through, so they understand the most optimal way to design the data center for NVIDIA. And we're also working with everybody on this call, with the AEC community, the engineers and EPCs and construction companies that are designing and building these data centers, so that they know, so that you know the most optimal way to do that. And we're also working with the companies who are building these data centers so that they know the same thing. So it's 3 in a pod, 3 in a box: the folks building the data center, the folks doing the engineering and construction, and all the MEP component vendors. We're all working together so we can build the right NVIDIA data center.
That's pretty cool, Sean, that like for an industry that maybe had a little bit of a public perception of like, right, construction, rough, tough, and dirty, it's at the center of like the AI revolution. Because if you guys, right, if you can't get the physical infrastructure online fast enough to do what you have to do, progress slows, right?
Not only slows, I mean, if some of these data centers are $50 billion to build and deploy. If every day of delay is like, you could look at your construction costs for delay. Oh, I'm losing $1 million a day or whatever. But from the opportunity cost, the loss of revenue that for every day you're down, it's $100 million on a $50 billion data center. So you can't afford a delay to turn that thing on. Just the same way you can't afford poor conversion of power to electricity. The other element is the ability to scale, because NVIDIA's released a multi-year timeline. So our customers are going to plan to expand the data center with our new technology. Like, here's what they're going to do this year, but they want to expand next year with the next generation, expand the year after with the next generation, so on and so forth. So the data center needs to evolve. And so we have plans for that. We actually have a 1,000-page reference design for how to build this type of data center. And of course, we have a method of doing digital twins so that there's no surprises. You're not just going to plug in the computers to the power and the cooling and turn them on and find out, oops, we made a big mistake on our $50 billion data center. No, everything is going to be simulated before, there's an ounce of concrete poured.
And which must make you guys a really sophisticated but respected owner and partner to these, right, to the rest of the community. Because, and how many times are construction projects essentially viewed as like exercises in a low bid? But for what you guys are trying to accomplish, right, that gets thrown out the door completely, because it's not about that. There's so much more to what you're trying to accomplish by, building a data center.
Yeah, and just for clarity, we build we do build data centers based on this reference design that I'm talking about, but we don't operate data centers for customers. It's just for ourselves, just to test out our hypotheses and for our own internal consumption of compute. But otherwise, this is all for partners. NVIDIA is partner first. So we're doing all this work to help our partners build better data centers. So the companies that are buying all that NVIDIA equipment through partners like Dell and Supermicro and Hewlett Packard and Cisco, they have the best return on their investment. So we're not the customer necessarily. It's our partners who are the customers, and we want them to be successful.
Absolutely. So, Sean, I just want to say thank you again for your time today. This has been great. So we'll close with one final question here. So, simply put, if firm leaders could start by improving one thing to strengthen project outcomes, where should they start?
Well, learn AI, like anything you can do to start learning AI, and think about, when you're hiring people, think about how those people coming in can bring that AI intelligence. And as you go through this process, educate up, because often, the folks at the top, they've been doing this a long time, may not know as much as you about AI. And believe me, because I talk to all of them, they want to know, they want to learn. So like if it's internal offsites, if it's lunch and learns, whatever, they want to understand use cases, what innovative thing you can apply AI to. There's lots of information out there at NVIDIA. My team, we try to share example use cases and customer success stories as much as possible. If you have any that you haven't seen on NVIDIA's website and you want to share with the world, ping me and we'll get on the call. And I'd love to learn about what you're doing with AI and try to get the whole world to understand how AI is going to just change our world.
Absolutely. And Sean, thank you again so much for your time. If the listeners want to connect with you again, like shoot you a message, ask you questions, what's the best way for them to reach you?
My email, seyoung@nvidia.com. And also, there's really cool stuff you can play with on NVIDIA's website. The first one is build.nvidia.com. We have a whole bunch of AI tools, models, and information. And you can actually, I think you get about 20 hours of free model experimentation time, either through APIs or just doing inference directly on our website on build.nvidia.com. And we have a huge amount of software tools available at developer.nvidia.com. And that includes all the Omniverse things we talked about, the Vision AI, which is Metropolis, our Cosmos world model, which understands the world through a camera, and lots of goodies. Too much to get into in the 1 minute we have left, but it's all up there. Developer.nvidia.com.
Speaking of, as someone, right, when we first met about a year ago, who's visited your guys' HQ, right, absolutely beautiful, lovely place. The simulation aspect and everything you guys were able to show us, top notch. So I would highly recommend taking Sean's advice and checking out what NVIDIA's got going on their website. But Sean, thank you again so much for your time. We really appreciate it.
Thanks, Nick. Great chatting with you.
Until next time.
Okay.
Likewise.
Bye-bye.
Please remember, you can find the show notes for this episode at aectechpodcast.com. There, you'll find a summary of key points discussed in today's episode, as well as links to any of the resources, websites, or books mentioned during the episode. Until next time, I wish you the best in all of your engineering and technology endeavors.